Well, all right, here we are. Well, here I am. So here's what I'm proposing to do with this first video of the week. This is our sample midterm. Now, I've actually posted the solutions online, so you can read them if you want to, but I would also like to go over them with you step by step so you can see what's happening just in case there's a problem, if you're not quite sure where the answers came from or how they were derived. So we'll go over right now. Now, this week I'll be, as you know, sending out a series of videos to take the place of our normal weekly meeting or nightly meetings, I should say. Now, I can't predict in advance how long each one will be. I'm going to try to keep them as coherent as possible. So, but each one might only be a fraction of our normal meeting time. So if that happens, I will label them appropriately, part one, part two, part three, that type of thing, so that it should be clear from the titles of the videos what exactly we're covering here. So first I'll start with the sample midterm. And then what I want to do is cover at the very least chapter 4B, and then as much of 4C as possible by the end of the week. Okay. And then of course, next week, we're going to have our normal sessions, except it turns out that Monday is the 4th of July. So we'll skip that night. And then we'll have two normal sessions next week on Tuesday and Thursday. And then we'll be right back on track. Okay. So in the meantime, we'll start with the first question. Now, these questions were taken from the book. And so the first one asks us to state the domain and range. And then it gives us a series of equations. This first one was x squared plus 2x plus minus 3 rather. Okay, so that's all they need for us to do. So first things first, since f of x is a polynomial, this guarantees that the domain is all real numbers. Okay, remember what the domain is. It basically is the list of x's that may be substituted into this equation without causing division by 0 or possibly a negative square root. So that there is no x that could cause a problem here. So the domain is simply all real numbers. Now, the range, if you recall, there is a formula for that. So first thing, let's remind ourselves that with the quadratic equation, we have ax squared plus bx plus c. And in this particular case, a is 1, b is 2, and c is negative 3. Okay, so the formula is this. The formula for the range, when a is positive, you might recall this from chapter 1, the range is the semi-open interval, as it's called, of f of negative b over 2a, comma, infinity. Okay, in other words, because what's happening is that we have something like this. The fact that a is positive means that the parabola is facing upward. And if you want, you can go to Symbolab and have it show you the exact form of this graph. This is good enough for us right now. And so that means that we're looking at, as the lower limit, negative b over 2a. Hold on a second. Trying to make sure I've got enough room so you can see everything. All right, here we go. Minus 2 over 2 times 1. So what that means then is that the lower limit of this range is f of negative 1. All right. Now, since the original equation was this, that means that f of negative 1 It's -1 squared plus 2 times -1 minus 3. So we end up with 1 minus 2 minus 3 minus 4. Okay, so ultimately that means that the range is -4, comma, and now the fact that this is a square bracket means that this is in fact included in the interval. And then we have infinity, which I can get from my symbols menu here. And that's it. Okay, and you can see why. So notice if you look at this picture, if you can imagine that the minimum point is down here somewhere. Actually, it looks like I haven't drawn it right, doesn't it? Hold on 1 second. Yeah, that's right. -1, -4. The parabola will not fall below there. So in other words, it's not possible for y to retain a value in this function any smaller than -4. So that's our range. Okay, so now we're going to do something similar for the function g equals log of x minus 5. Now, as far as this one is concerned, in fact, I'll tell you what, for something like this, why don't we draw a picture of it, or at least have Symbolab draw a picture, because it's just easier to visualize what's happening. You know, sometimes the graph can make a huge difference in our understanding of the range in the domain. I mean, we can certainly calculate them, but I think having a picture makes a huge difference in our ability to understand what this is telling us. Ooh, now look at that. Oh, interesting. In fact, let me grab that. You can see that the x equals 5, the vertical line x equals 5 is an asymptote. So, but if you notice, as far as the x's are concerned, the x's do not include 5 itself. The log of 0 is undefined. And so are negative logs. You cannot have a negative log. A log has to be non-negative. So that means that the domain rather starts at but does not include 5. In other words, it's 5, everything above 5, but not including 5. And then, of course, it goes up to infinity. So x can go all the way out here. The range, though, if you notice, if you look at the vertical axis, y can attain any value. So it's negative infinity up to positive infinity. In other words, there's no value that cannot come out of this function. Okay. All right, and then the third one was h equals 1 over x plus 4. I think it should be pretty obvious that x cannot equal -4 rather, because that would give us division by 0. So basically, we don't even have to draw a graph of this. The domain is everything except -4. And you'll recall that we write this as the union of two intervals from negative infinity up to, but not including -4. And then we combine that with not everything above -4, not including -4 up to infinity. The range is a little different. Matter of fact, I'll tell you what, let's go do the graph, just so we can see this. The range will basically be everything except 0. All right, let's try that. 1 over x plus 4. Oh, now that's a complicated one, but you can see that it actually has two asymptotes. One vertical, one horizontal. So as far as x is concerned, you can see this vertical line is -4, although sometimes it's hard to tell when the way they label these things. So x can be anything but -4, and y can be anything but 0. Okay, that is the horizontal axis. That is our horizontal asymptote. So that implies that the range is everything but 0. Now, Symbolab can do this for us too. It tends to use different notation. Oh no, they use both. Okay, so they agree with us. They're just basically saying that x can be anything but -4. Y can be anything but 0. Okay, that's that. All right, now the next question is 123.16. And for that one, we have a composite function. All right, we're told that f of x is x squared plus 2x minus 3. And h of x is 1 over x plus 4. So they want to know. Now they're writing it like this in the question, but keep in mind, this is the same thing as h of f of x, which means you're taking your h of x and you are replacing all the x's with f of x's. I guess technically that should be f's of x. I don't know. It's hard. We should find out from an English person, an English major, if what is the correct way of pluralizing f of x. That would be interesting to find out. But anyway, so you're going to have so you basically have just replaced the x in this equation with f of x. And now you just rearrange this slightly. And that's it. That's all you have to do. Okay, I like those. All right, for 318, same page. They're asking us to find 3 things. Find the degree, y-intercept, and zeros, which means solutions, for. So the function is f of x equals 2x squared plus 9x minus 5. All right, the degree is easy. Okay, this is the highest exponent of x in the equation. So that's the degree. The y-intercept occurs. Remember what that means. The y-intercept, in fact, why don't we look at a picture real fast? 2x squared. So we can visualize what it looks like. 2x squared plus 9x minus 5. Okay, in other words, this is what they're looking for right here. Where does it cross the y-axis? This is the point where x equals 0. That's the key to the whole thing. So what we're looking for is f of 0. Okay. So that's clearly equal to -5. And that, you can tell by looking at the graph, that looks about right. This is the point 0, -5. This is the y-intercept. Now the zeros. Now for this one, we can use factoring or the quadratic formula, since this is a quadratic equation. All right, let's go get it back. So it doesn't look like factoring is going to help. All right, so what the heck? Let's just use the quadratic formula. That doesn't mean we couldn't factor. I'm just saying that it might be easier to simply use the quadratic formula. Usually when the coefficient of x squared is not 1, factoring becomes a real headache. And then you might as well just use the quadratic formula. Is not that difficult. In fact, as far as I'm concerned, I really don't know why you would ever want to factor anyway. I think the quadratic formula is so simple. Now, of course, Symbolab can do this for us, but we need to know how to do it ourselves. So we're going to plug in these numbers. All right, what do we have? Well, now it looks like we're in luck. 121 is a perfect square. May not be that obvious, but it is, because that is the square of 11. Okay, so those are the two solutions. That means that we should find on the graph that the graph crosses the horizontal axis at the points 5, -5 rather, and a half. And again, sometimes it's hard to tell with these Symbolab graphs, but it does look like this is -5 and this is 1/2. It's halfway between the 0 and the 1 on this graph paper that they're giving us. So this is definitely correct. So the solutions or zeros are where it crosses the horizontal axis. Okay, now that was 318. On page 121, number 320. Oh, trig. Okay, don't worry, this one isn't as bad as it looks. They're asking us basically to simplify tangent squared x over secant squared x plus cosine squared x. Now, of course, they obviously expect us to use identities to help reduce it to something more simple. So let's write down the definitions of these. You might recall tangent of x equals the sine over the cosine. The secant is the inverse of the cosine. So if we plug those in, by the way, because of these identities, let me just mention one thing here. Since these are true, that implies that the tangent squared of x equals the sine squared of x over the cosine squared of x. It also means that the secant squared of x equals 1 divided by the cosine squared of x. So we're going to wind up with so I've replaced tangent squared of x with sine squared over cosine squared, and then secant squared was replaced with 1 over cosine. Now, we want to certainly simplify this first term. So here's how we can rewrite it. Divided by 1 over this is the same as multiplying by cosine squared over 1. And this is the key to the whole thing, because all of a sudden we have sine squared x plus cosine squared x equals 1. That is one of the Pythagorean identities. I've got a bunch of them. One of the chapters has a whole slew of these. It's actually 1C, I remember, because that's where all the trade material is. It's definitely in there. There's a lot of them, but that one you should be able to memorize it. That's one of the few that you really should have on the tip of your tongue. Oh, there's so many of them, but that's the one that is one you might want to hang on to. Now, by the way, if you just throw this into Symbolab, it'll come back with the 1. Okay, 324. So far, these aren't too painful, are they? There's a couple of really tough ones coming up later on, but even then, we break it up into little pieces and attack it separately. You'll see that they're not that difficult either. Now, here's an interesting case. Whenever you have x in the exponent like this, the first thing you should always think of is, I probably should use logs. Okay, and you're right, because logs will help us simplify something like this. So just remember, the log of x to the n is n log x, and the base doesn't matter. But what we need to do here, it doesn't matter what log we use. We're allowed to take the same log of both sides of an equation without affecting the results. So this can be rewritten as x log 5 equals log 16. And then when you're done, all you have to do is this. That's it. Now, if you need the specific numerical value, you can certainly do that. But for here, we can just leave it like this. Okay, now this next one. I'm not so sure if I should have picked this one. This is number 212, only because we're going to have to go to the book and grab the diagram. Otherwise, we won't know what in the world is going on. So hold on one second. They're asking us to take limits, but not based on equations, but on from a diagram that's actually in the book. So hold on one second while I get it out. Oops, I think I just went right past it. Here we go. Yep, here it is. Okay, you see what I mean? It's a very tricky little graph, which I will not attempt to draw. All right, so for the limit of -1, so you can see what's happening here. As we approach from the left, the function is getting very close to 1, but as we approach from the right, we're getting close to -2. So this one does not exist. Because the limit, as x approaches -1 from the left, does not equal the limit as we approach from the right. Okay, so that means it does not exist. Now, the next one is for +1. +1 is a tricky one because you see what's happening is that as we approach from the left, it appears to be approaching 1, and the same thing's happening as we approach from the right. It approaches this hole. Now, even though there's a single point here, you might say to yourself, well, the fact that there's this gap here with a hole and this other point should mean that there's no limit, but that's actually not the case. The limit, as x approaches 1, is just 1. In other words, they're both converging and getting very close to this hole. And so that actually is the limit. That's considered to be the limit in spite of the existence of this point down here. That is the correct limit for this thing. So essentially, I mean, you have to think about the limit as what's happening as we approach from the left and the right. If they're both approaching the same point, whatever that point is, that's the limit. Okay, now see, this one is specifically about approaching 0 from the right. So as we approach from the right, we're coming this way. And because we're only interested in the right, that's equal to 0. Now, coming from the left, you can see we're getting to -1, and that means this limit doesn't exist. The two-sided limit does not exist. But the limit as x approaches 0 just from the right is in fact 0. And then the last one, the limit as x approaches 2, so actually I better get some of this stuff out of here. Now there's a problem with this one. What is the problem? As we approach from the left, fine, the limit appears to be 1 from the left, but the function is undefined for any values of x past 2. So the limit coming from the right does not exist. And so therefore, this does not exist either. Okay, in other words, the limit as x approaches 2 from the right does not exist. And so therefore, the full limit, the two-sided limit cannot exist. All right, so that one was kind of a tricky one. Now we got some limits. You can see we're in the chapter 2 section. The next question is, to go back to the top here. That was 212. The next one is 214. Okay. Now 214. Oops. Asks us for I have it written down here somewhere. Here it is. The limit as x goes to 0 of 3x squared minus 2x plus 4. Now, for this one, we can just plug everything in. The 0 does not cause any problems in this case. So we just, with direct substitution, we come up with 4, and it's just that simple. Okay, it's often not that simple, but in this case it is. Okay, direct substitution led us to the answer. Okay, as long as it doesn't lead to division by 0 or something like that, we can always use direct substitution. But 218 is a little different. 218, we have a problem. 3x squared minus 2x minus 8, or x minus 4. Sorry, x squared minus 4. We can see where the problem is here. Oops, hold on. So direct substitution gives, yeah, I think you can see where this one is going. 3 times 2 squared minus 2 times 2 minus 8. 2 squared minus 4. Yeah, it's 0 over 0. Okay, now later on in the book, not in this chapter, chapter 2, we were not introduced to L'Hopital's rule just yet. We know already that L'Hopital's rule can be used when we end up with 0 over 0, but here we hadn't got to that point yet. So what we can do instead is we can see if there's any way to factor that ratio and simplify it so that we no longer have to deal with 0 over 0. Now, you know, in chapter 4, we certainly can use L'Hopital, but here we hadn't gotten to that point yet. So what they meant for you to do was look for opportunities to factor. Now, if you look at the denominator, that one's pretty straightforward. What about the numerator, though? You might look at it and say, well, I can't tell if it has any ways of being factored. So here's what we're going to do. We're going to use this technique called long division to see if maybe I can divide one of these factors into the original equation. Well, let's find out. Now, you might not remember how to do this. It's just like regular long division. What I'm going to do is start with 3x. Because if I multiply this term by 3x, I get 3x squared minus 6x, sorry, 6x. Okay, so what did I just do? 3x is multiplied by x minus 2. It gives me 3x squared minus 6x. Now I have to subtract that entire expression. To be super careful with the signs. These drop out, this becomes positive, and end up with 4x. I bring this one down. Now let's try 4. 4 times x minus 2, oh my God, it worked. So what this means is that the numerator let's copy this again. Can be written as x minus 2, 3x plus 4. Well, that helps a lot because all of a sudden, the original expression can be rewritten as x minus 2, 3x plus 4 x minus 2x plus 2. Well, there you go. That's the solution to our problems, because now we have and now direct substitution works out beautifully. 5/2. Ta-da! So yeah, the whole idea here is to simplify. Okay, when you end up with division by 0, it doesn't even have to be, as long as there's a 0 in the denominator. L'Hopital requires 0 over 0, but as long as you have 0 in the denominator, you can always try to factor. Okay, now 220, we have a similar problem. It looks worse. When you see it, you'll say, oh my God. Limit x goes to 1, x squared minus 1, radical x minus 1. Now, whenever you see a binary term involving radicals, by the way, let's just double check that direct substitution leads to 0 over 0, or at least division by 0. So what we're going to do now is simplify. There's a very specific technique we're going to use. And it's called rationalizing the denominator. And how do we do that? Well, remember, we introduced this concept a while back. These are known as conjugates of each other. So here's what we're going to do. We'll take this expression and multiply it by radical x plus 1 over radical x plus 1. So we'll end up with in the denominator, when you do something like this, you're going to wind up with the squares of the first term minus the second term. And you see the beauty of this is that x squared minus 1 can be broken down into x minus 1, x plus 1. So therefore, we have something where we can solve for a direct substitution. So the limit of this expression is 4. Now, if you throw this into Symbolab, it will give you the answer. Sometimes it'll give you all the steps. Sometimes it won't. Sometimes it expects you to have paid a subscription. So what I did, by the way, here's what I did. I realized that it's not very expensive to get a subscription to Symbolab. So I went ahead last night and I ordered a subscription. So going forward, whenever we need to see more detailed results on Symbolab, we can do it because I've paid for the subscription and now I can look at them. I don't know how much of a difference it's going to make, but it's good to know that it's there if you need it. If you need more explanation, it's like $35 for the whole year or something like that. So that's that. All right. Now, what was next? There's another. That was 220. So 222 is, a ridiculously simple one. It's amazing how sometimes they're so easy and sometimes they're so hard. The limit as x goes to 4 of 1 over 4 radical x minus 2. What's so hard about that? All you have to do, yeah, they just slipped that one in there on us. Hold on, the marker's giving me trouble. Okay, here we go. No, it's doing the same damn thing. Sorry, I'm having technical difficulties here with the pen. You notice I'm writing with a tablet here, and this marker, sometimes if your finger hits the wrong button, it just makes these horrible. I don't know why they would even let this be an option. God only knows what these idiots were thinking of. Why would I want that? No, it's still doing it. God damn this thing. It's just like, what purpose does that serve? I can't turn it off. It's a little button on the side so that you're guaranteed to hit it by accident every so often. It's very poorly designed. Very poorly. No, it just won't stop. No. I'm going to throw this thing out the window any minute now. I'm telling you. It's just like there's 2 buttons on here. You'd think one of them would turn it off, but no, that would be too simple. No, that's it. It's just stuck. I guess I'm stuck with this forever. No. All right, well, I'll tell you what, I have to stop now here anyway. I'll just verbally tell you that if you plug in the numbers, you'll end up with 1/6. Okay, I'll see what I can do about fixing this wretched pen here. But that, yeah, so I have to stop right here for now. So let's think of this as the part 1 of our review. The next section, I should be able to finish the rest of them, but if you want to look ahead, like I said, I've already posted the actual typed up answers, so you can go ahead and look at them. But I think that there's some benefit to doing this step by step anyway. So if you watch this, you can see exactly what's going on. So very soon, I will post another video with the rest of this, and then later on, I'll do 4B, which is our new material. So anyway, so I'll see you again soon. So I hope you learned something from the session, and I'll see you very soon.